We are now at question 9 of the CXC CSEC January 2014 General Paper 2 exam video solution. And we are starting with question 9a, which is a functions question. And in this functions question, we are given two functions. H of x is equal to 10 divided by x minus 3. And we are also given the function g of x, which is equal to 3x minus 2. And part 1a wants us to evaluate g of 4, and part B wants us to evaluate h of g of 4. Let's do g of 4 first. Now g of 4 is obtained by simply substituting 4 in the g function, and this is it. G of 4 is equal to 3 multiplied by 4 minus 2. We get this simply by substituting 4 for x in the g function. And when we do this calculation, we get 3 times 4 is 12, and we are subtracting 2, and so 12 minus 2 is 10, and so that's the answer for that part. G of 4 is equal to 10. Part B now wants us to find h of g of 4, and h of g of 4 may be written as h of g of 4, but we have already calculated g of 4 to be equal to 10. So this h of g of 4 is simply equal to h of 10, because we already know that g of 4 is 10, and now h of 10 is obtained by substituting 10 for x in the function h, and when we do that, the result is 10 divided by 10 minus 3. We obtain this by replacing x in the h function with 10. That's how we calculate h of 10, and when we do this calculation, we get 1 minus 3, because 10 divided by 10 is 1, and we are subtracting 3. 1 minus 3 now is equal to negative 2, and therefore h of g of 4 is equal to negative 2. And that's the answer for part 1. In part 2 now, we're asked to firstly derive h to the minus 1 of x, and then in part B, we want g of x. Now, h to the minus 1 of x is the inverse of h of x. And the relationship between h of x and h to the minus 1 of x is that the domain of h of x is equal to the range of h to the minus 1 of x, and the range of h of x is equal to the domain of h to the minus 1 of x. That is, there's an interchange of the domain and the range. And so, to calculate the function h to the minus 1 of x, it's a simple case of interchanging the representation of the domain with the representation of the range. And this is it. H of x represents the range of this function, and x here now represents the domain of the inverse function. And so the range of the function becomes the domain of the inverse function, and the domain of the function here becomes the range of the inverse function, and the range of the inverse function is represented as h to the minus 1. And all we need to do now to find h to the minus 1 of x is transpose this formula to make h to the minus 1 the subject. And so we can proceed firstly by adding 3 to both sides. We will move the negative 3 from this side by adding 3 to both sides. And when we do that, we end up with this. X plus 3 becomes equal to 10 divided by h to the minus 1. And x plus 3 here is the same as x plus 3 divided by 1. Now, we want to make h to the minus 1 the subject, and so we can multiply that across here. Let's show that. And that's it. And we are left with 1 under here. And then, to get rid of this x plus 3, we divide both sides by x plus 3, or we say we divide the x plus 3 down on this side. And so let's show that. And that's our result. Now we have h to the minus 1 divided by 1 equals 10 divided by x plus 3. And now that reduces to h to the minus 1 equals 10 over x plus 3. And that's our inverse function. And h to the minus 1 is a function of x. And so we can put the notation for a function of x there. And that is it. H to the minus 1 of x is equal to 10 divided by x plus 3. And this inverse function will map the range of this function back onto the domain of this function. Part B now wants us to calculate g of x. That is the composite function of g on itself, and this is it. G of x can be written as g of x, and to calculate this composite function we can substitute g of x into itself, and this can be viewed as substituting g of x for x here. And when we do that, this is the result. The x here is being replaced by g of x here, and so the x here is replaced by g of x on this side, and so g of x becomes 3 times g of x minus 2. We have simply replaced the x in g of x here with g of x, and since g of x itself is 3x minus 2, we can now substitute 3x minus 2 for g of x here. So let's show that, and this is it. And so this reduces to 3 multiplied by 3x minus 2 minus 2. And we can proceed now by simplifying this expression, and this is it. 3 multiplied by 3x is 9x, 3 multiplied by negative 2 is negative 6, and we have negative 2 coming back here. And so that reduces to 9x minus 8. And so that's the answer for this part. Let's move down to part B of question 9. Now question 9b gives us this quadratic function y equals x squared plus bx plus c over the interval negative 2 to 6. That's the domain. And this is a graph of that quadratic function. And we observe for this quadratic function, we are given the intersection with the x-axis, and we're also given the intersection with the y-axis. And in this question, we are going to be required to calculate the value for b and the value for c. But let's talk about the quadratic function a bit. Now, the quadratic function can be expressed in 3 basic forms. This form is called the standard form, this form is called the factor form, and this form is called the vertex form. And each form of this quadratic function gives us information that the other forms cannot. And from this standard form, we can go to this factor form by the process of factorization, and we can also go from this standard form to this vertex form by completing the square. And if we compare this standard form with the form for this quadratic expression that was given, we see that our a value is equal to 1. And so we can show that our a value is 1. But let's talk about the information that we can get from each form of this quadratic function. Now this, as I said, is the standard form. And this form gives us information about the shape of the quadratic graph and also the location of the y-axis intercept. When the a is positive, the quadratic graph will have a smile shape, as is the case here, but when the a is negative, the graph will have a frown shape. The c here is the value of the y-axis intercept. That is the point where the quadratic graph intersects the y-axis, because on the y-axis, the x value will be 0. And if the x value is 0, then y will be equal to c. And so the standard form gives us information about the shape and also tells us the location of the y-axis intercept. This factor form, as I said, is obtained by factorizing the standard form, and it gives us information about the location of the points where the graph intersects the x-axis, and those points of intersection with the x-axis are called the roots. And so R1 would be the x value at the point of intersection of the x-axis here. That's a smaller value of the two roots. And then R2 would be the x value at this larger root. And so in this case, R1 would be equal to -1 and R2 would be equal to 5. This third form is called the vertex form or the turning point form. And when we complete the square of the standard form, it can be written into this vertex form. This vertex form gives us information about the vertex of the quadratic graph. And that's it. It tells us the location of the turning point. When the a is positive, the turning point will be a minimum turning point. But if the a was negative, then the turning point would be a maximum point. And the coordinates of the turning point can be extracted from this form xt, yt. xt is the x value at the turning point here, and yt is the y value at the turning point here. And xt and yt can be derived using the constants a, b, and c, and we'll see that later. Also, the vertex form tells us the axis of symmetry of the graph. The quadratic graph has an axis of symmetry that divides the curve into two halves such that one half is a mirror image of the next. And this axis of symmetry passes through the vertex where the x value is xt, and so the equation of this axis of symmetry, which is a vertical line through the turning point, is x equals the xt value. And so the vertex form gives us information about the turning point and also tells us the equation of the axis of symmetry. So we see the relevance of being able to write the quadratic function in the three different forms, because each form provides information that the other two forms cannot. But let's move down now to the questions. Now the first part wants us to state the roots of this quadratic equation. Now this is a quadratic equation that is associated with this quadratic function, and the quadratic equation is associated with the point where the graph intersects the x-axis because it coincides with y equals 0, which is the equation of the x-axis. And so when we solve a quadratic equation, the results are the x values where the quadratic graph intersects the x-axis. And so the solution of this quadratic equation would be the two roots of the quadratic function, and that is the x value here and the x value here. And so the solution for that quadratic equation would be those two root values, x equals -1 and x equals 5. And so we can write that the solution for this equation, which are called the roots of the quadratic equation, which is associated with this quadratic function, would be x equals -1 for here and x equals 5 for here. And that's the answer for that part. But now that we know the roots, we can substitute them in the factor form to derive the standard form, and we'll do that here. And this is it. The roots are x equals -1 and x equals 5, and using this factor form, r1 would be equal to -1 and r2 would be equal to 5. And so we can substitute -1 for r1 here and substitute 5 for r2 here, and our quadratic equation in the factor form would become this: x minus r1, which is -1, multiplied by x minus r2, which is 5, equals to 0. And that reduces to x plus 1 because minus a -1 gives us a +1 here. And we can now expand these factors to the standard form, and this is it. X multiplied by x is x squared, x multiplied by -5 is -5x, and then 1 multiplied by x is x, and 1 multiplied by -5 is -5. And when we reduce this, we end up with x squared minus 4x minus 5 equals 0. That is, -5x plus x gives us -4x here. The x squared comes back here, -5 comes back here, and so this is our quadratic equation. And now if we compare this quadratic equation with this, we see that b is equal to -4 and c is equal to -5. That is, plus b is equal to -4 and plus c is equal to -5. And that is one way we could use our root to derive the value for b and c. But let's move down to part 2. Now part 2 wants us now to calculate the value of c and the value of b. And we already have the value for c and b, but we will continue to look at other methods of calculating these values. And now for the value of c, we can consider the point where x equals 0. When x is equal to 0, y will be equal to c, and that coincides with our y-axis intercept. And the graph gave us our y-axis intercept as -5, and so c is confirmed to be equal to -5. For b, we have already shown that our quadratic function is actually x squared minus 4x minus 5. And so b is equal to negative 4, and we can therefore write that b is equal to negative 4. And that's the answer for that part. Part 3 now wants us to state the coordinates of the minimum point. That's the minimum point right here. And to find the coordinates of the minimum point, we could consider putting our quadratic expression in the vertex form. We already have the standard form where we know the value for b and c, and now we can consider putting our expression in the vertex form. And because the coordinates of the minimum point is xt, yt, our primary aim here now would be to calculate the xt, which is the x value at the turning point, and yt, the y value at the turning point. Now, as I said in the beginning, xt can be expressed in terms of the a, the b, and the c in the standard form, and yt also can be expressed in terms of the a, the b, and the c. And for this quadratic function, we have now concluded that a is equal to 1, b is equal to negative 4, and c is equal to negative 5. And the formula for calculating the x value at the turning point, xt, is negative b divided by 2a. xt, the x value at the turning point, is given by negative b divided by 2a, where b is the coefficient of x and a is the coefficient of x squared. We have b as negative 4 and we have a as 1, and so xt will be equal to minus negative 4 divided by 2 times 1. This minus comes back here. B itself is negative 4, and we are dividing by 2 times a, which is 2 times 1. When we do this calculation, the result is 2, and so the x value at the turning point here is equal to 2. The y value at the turning point, yt, the y value at the turning point, can also be calculated, as I said, using the coefficients in the standard form, and this is it. Yt can be calculated using this formula, 4ac minus b squared divided by 4a. And when we substitute the values for a, b, and c, it will give us the y value at the turning point, and this is it. 4ac becomes 4 times 1 times minus 5, because a is 1 and c is minus 5. This minus comes back here, and then we are squaring the b value. So we are squaring negative 4. And then we divide by 4a, which is 4 times 1. When we simplify this expression, we get negative 20 minus 16 divided by 4. That is, 4 times 1 is 4. 4 times minus 5 is negative 20. This minus comes back here, and then negative 4 squared is 16. Divided by 4 times 1 is 4. It comes down to negative 36 divided by 4. And negative 36 divided by 4 is negative 9. And so the x value at the turning point is 2. And the y value at the turning point is negative 9. And so we have the coordinates of the minimum point. And this is it. The minimum point has coordinates 2, negative 9. And that's one way we could have found the coordinates of the minimum point. Let's look at another method which would involve the use of the roots. And this is it. In this method, we will consider the fact that the graph has an axis of symmetry. And so this line divides the graph such that one half is a mirror image of the other half. And so the two roots are symmetrical about the axis of symmetry. And so the distance from this root to the axis of symmetry is equal to the distance from this root to the axis of symmetry. And since the axis of symmetry is a vertical line to the minimum point, it means that the x value at the midpoint between these two roots coincide with the x value at the minimum point. And that is it. And so xt is the midpoint between negative 1 and 5. And so xt can be calculated using the average of the two roots. And this is it. Xt is equal to negative 1 plus 5 divided by 2. The result is x equals 2, as we got from the first part. Now that we have the x value at the turning point, we can find the corresponding y value at the turning point, which is yt, by substituting the x equals 2 into the quadratic function here. And this is it. Because yt is a y value at the minimum point when x equals xt. And so by substituting the xt value in this function, we will calculate the yt value here. And this is it. Yt will be equal to 2 squared minus 4 times 2 minus 5. We have substituted 2 for the xt value because xt is equal to 2. And when we do this calculation, we get 2 squared is 4 minus 4 times 2 is 8 minus 5. And this reduces to negative 9. And so yt is equal to negative 9 as we had before. And so the xt value is 2. That's the x value at the turning point. And the yt value is negative 9. And so the coordinates of the minimum point is confirmed to be 2, negative 9. And so that's the answer for part B of question 9. And that's the end of question 9. And we'll do question 10 in the next video. See you then.